Hi there, and welcome to this lecture on process flow diagrams, equipment summary tables. My name is Marina Milicic. Over the past few lectures, we've discussed the required tables which supplement every process flow diagram. We looked at stream or flow summary tables, as well as utility stream or utility summary tables. But there's another critical table which must be provided as a supplement to every process flow diagram, and that's an equipment summary table. Equipment summary tables provide critical physical characteristics for each piece of equipment that has a letter and number designation on a process flow diagram. This information includes the type of equipment, the equipment's height, width, volume, or area, its power output or generation, the material the equipment is constructed of, the incoming and outgoing temperature and pressure, among other information. This information is critical because it enables us to look in books, catalogs, call up distributors, or use price estimation software to determine not only the initial cost of purchasing that piece of equipment, but also the cost of running it. Recall that these costs are instrumental in determining the initial and ongoing expenses of the process, and if these outweigh the money generated from selling the product, then the project should not be continued. This is an equipment summary table for the ethylene oxide production process. Some equipment is listed in groups. For example, compressors, turbines, and pumps are all listed together. And the same is true for vessels, towers, and reactors. However, heat exchangers and fired heaters are grouped by themselves. Every piece of equipment with a letter and number designation on the process flow diagram is described in this table. Let's start with compressors, turbines, and pumps, and look at the information you should provide for these units. One of the first pieces of information you should provide is type. Though there are many choices, there are four general types of compressors, turbines, and pumps: axial, centrifugal, reciprocating, and rotary. Axial is the most common type of compressor and turbine for large chemical processes with high flow rates. Centrifugal is the most common pump type used in large chemical processes. In almost all cases, this design is the cheapest, most efficient way of increasing the pressure of liquids for low viscosity, high flow rate applications. Reciprocating compressors and pumps usually use pistons connected to a crankshaft to increase pressure through back and forth motion. Reciprocating compressors, pumps, and turbines are also sometimes called positive displacement, and they're typically used for smaller applications requiring minimal space and involving low flow rates. Rotary compressors or pumps usually compress by physically shrinking the size of the gas or liquid cavity, forcing the fluid into a smaller volume using some form of rotation. Rotary compressors or pumps are also sometimes referred to as positive displacement and are frequently used when high viscosity or non-Newtonian fluids need to be pressurized. Something that surprises most students is that ChemCAD or Aspen will not select a compressor, turbine, or pump type for you. I suggest you look in a design book and determine the best type based on the flow rate, the horsepower required to run the compressor or pump, the inlet and outlet pressure of the process stream, and the price. For this ethylene oxide process, I chose reciprocating for the compressors because it's the cheapest for their power requirement, axial for the turbine because almost all turbines are an axial design, and centrifugal for the pump because it's the most efficient and cheapest for the flow rate and power required. Once you've selected a compressor or pump type, it's important to select the drive type. The drive is what actually creates the motion which runs the compressor or pump and enables it to pressurize the fluid. Recall that turbines actually extract energy from a fluid through depressurization. Instead of the fluid having work done on it, here the fluid is doing the work to create rotation or movement. So because energy is not being added to the fluid, but instead being removed, turbines don't have drives. There are four main types of drives you can choose: electric, steam turbine, gas turbine, or internal combustion engine. Let's start with the most common, electric drive. Many process compressors and pumps are run using an electric drive, more commonly referred to as an electric motor. Electric motors are the most common drive type in most chemical processes because they have high efficiencies and work well when the power requirement is 100 horsepower or lower. Steam turbines create motion by sending steam through a turbine, which generates rotation, which is then used to run the pump or compressor. Though they're less efficient than electric motors, steam turbines are useful when the power requirement for a pump or compressor is greater than 100 horsepower, and during power outages to help keep the process running. Gas turbines differ from steam turbines in that instead of sending steam through the expander, some other gas or vapor is used. The disadvantage with gas turbines is that they tend to be very inefficient and expensive, but they may pay for themselves in the case where a high flow rate gas stream would need to be depressurized anyway. In this case, if enough power is generated, gas turbines are well worth the initial and ongoing cost. Lastly, internal combustion engines combine a fuel, such as diesel or gasoline, with air and compresses the mixture, then combusts it, usually in a piston and cylinder system. Internal combustion engines are sometimes used to run pumps or compressors in remote areas or where availability to electricity is intermittent. The disadvantage of using them is that they tend to be very inefficient since a lot of energy is lost to heat and the fuel source always needs to be replenished. So to select the best drive type, consider the horsepower required by the pump or compressor. Remember that electric drives are typically more efficient than steam turbines, which are more efficient than gas turbines and internal combustion engines. And try to find the option which results in the lowest long-term cost. You can find estimates of power ranges, efficiencies, and prices in most process design books. Because of their high efficiency and low cost, I chose electric drives for these compressors and the pump. Remember that turbines do not require a drive because they're used to depressurize or extract work from a fluid. This is why there was no drive type selected for turbine C103.